During the setup phase, what is the primary clinical rationale for utilizing a balanced crystalloid solution, e.g., plasmolite, over normal saline, 0.9% NaCl, for the circuit prime? A. Normal saline causes severe systemic vasodilation on bypass. B. Large volumes of normal saline risk inducing hyperchloremic metabolic acidosis. C. Balanced crystalloids prevent the degradation of the circuit's biocompatible coating. D. Normal saline has a higher viscosity, which increases workload on the pump. Answer: B. Large volumes of normal saline risk inducing hyperchloremic metabolic acidosis. Explanation: Normal saline contains a supraphysiological concentration of chloride, 154 milliequivalent/L. Priming a CPB circuit with large volumes of 0.9% NaCl causes a dilute drop in bicarbonate concentrations and excess chloride load, routinely inducing hyperchloremic metabolic acidosis. Balanced crystalloids match physiologic pH and electrolyte concentrations, preserving acid-base stability upon initiation. While running a centrifugal arterial pump on CPB, the perfusionist accidentally leaves the arterial line completely clamped when starting the pump. What is the immediate structural consequence inside the circuit? A. The arterial line will violently rupture or burst off its connectors. B. The pump will generate a high vacuum, causing the venous reservoir to collapse. C. The pump head will spin harmlessly at its maximum pressure capability, hydrostatic deadhead, without line rupture. D. The oxygenator membrane will instantaneously tear open. Answer: C. The pump head will spin harmlessly at its maximum pressure capability, hydrostatic deadhead, without line rupture. Explanation: This highlights a key safety distinction between pump types. A roller pump is a positive displacement pump. If clamped, it will continue forcing volume forward until the pressure blows a connection apart or ruptures the line. A centrifugal pump operates via magnetic coupling and kinetic energy. If clamped, it reaches a maximum deadhead pressure threshold where the blood simply slips on the spinning cones, preventing catastrophic line explosion. Which phenomenon describes the dynamic drop in systemic oxygenation that occurs if the gas flow channels within a membrane oxygenator become obstructed by accumulated water vapor condensation? A. Cavitation. B. Shunt fraction elevation. C. Waterlogging or sweating of the oxygenator. D. Spallation. Answer: C. Waterlogging or sweating of the oxygenator. Explanation: As warm blood passes through the oxygenator alongside cooler sweet gas, water vapor naturally condenses within the gas pathways of the hollow fibers. Over time, this condensation can build up and physically block gas flow through portions of the bundle, waterlogging, decreasing the surface area available for gas exchange and causing an insidious drop in the patient's PA2. It is corrected by delivering a brief, high-flow gas flush to clear the moisture. When managing a patient with documented cold agglutinins whose antibody thermal amplitude is active up to 28 circ, what mandatory modification must be made to the CPB circuit and strategy? A. The circuit must be primed with ice-cold crystalloid to shock the antibodies. B. The patient and circuit must be kept strictly systemic normothermic, completely avoiding hypothermic strategies. C. The heat exchanger must be disconnected entirely to prevent temperature fluctuations. D. The blood flow rate must be halved to prevent shear stress activation. Answer: B. The patient and circuit must be kept strictly systemic normothermic, completely avoiding hypothermic strategies. Explanation: Cold agglutinins are antibodies that cause red blood cell agglutination, clumping, and hemolysis when blood cools below a specific trigger temperature, thermal amplitude. In such patients, systemic hypothermia or cold cardioplegia delivery can cause intravascular clotting within the patient and inside the CPB circuit fibers. Perfusion must be managed under strict normothermic conditions, 37 circ. What is the primary purpose of the cardiotomy isolation valve found on modern hardshell reservoirs? A. To isolate the arterial filter during an emergency swap. B. To separate the cardiotomy suction filter from the main venous reservoir, preventing air or defoamed fat from migrating into the venous pool during stable periods. C. To shut off the gas flow to the patient. D. To prevent retrograde flow into the left vent. Answer: B. To separate the cardiotomy suction filter from the main venous reservoir, preventing air or defoamed fat from migrating into the venous pool during stable periods. Explanation: blood gathered from field suction is highly inflammatory and contains defoaming chemicals and microdebris. The cardiotomy isolation valve allows the perfusionist to partition the cardiotomy section away from the main venous reservoir when field suction is not actively needed, minimizing the patient's continuous exposure to processed, activated shed blood. During CPB, an arterial line pressure monitor goes into an active alarm state, displaying a negative pressure, e.g., -20 mm of mercury, downstream of a roller pump head. What is the most likely cause? A. The patient's blood pressure is dangerously high. B. The arterial cannula has slipped entirely out of the aorta. C. The stopcock on the pressure transducer was turned incorrectly or the line is completely occluded upstream of the sensor. D. The oxygenator has developed a massive clot. Answer: C. The stopcock on the pressure transducer was turned incorrectly or the line is completely occluded upstream of the sensor. Explanation: a positive displacement roller pump pushes fluid forward, creating positive pressure downstream. The only way an arterial line sensor registers a negative pressure is if there is an physical occlusion before the sensor while the pump continues to pull fluid, or more commonly, a technical artifact such as an incorrectly oriented stopcock venting the transducer to an enclosed or closed system during sampling. If a patient experiences severe protamine shock, anaphylaxis, shortly after being weaned from CPB, what is the immediate circuit safety priority if the surgical team decides to resume bypass? A. Flush the entire circuit with normal saline before reinitiating. B. Re-administer a full systemic dose of heparin to achieve an ACT greater than 400 seconds before blood enters the circuit lines again. C. Spin the pump backward to clear residual protamine. D. Replace the membrane oxygenator immediately. Answer: B. Re-administer a full systemic dose of heparin to achieve an ACT greater than 400 seconds before blood enters the circuit lines again. Explanation: protamine neutralizes heparin to restore normal clotting. If a catastrophic protamine reaction occurs and the patient must go back on CPB, the blood is currently in a procoagulant or normal clotting state. Resuming bypass without reheprinizing would cause instantaneous, irreversible thrombosis of the entire CPB circuit the second blood contacts the tubing. Why is it dangerous to allow the venous reservoir level to drop too low when utilizing kinetic-assisted venous drainage, KAVD, via a centrifugal pump on the venous line? A. The pump will stall due to high systemic resistance. B. The negative pressure will pull massive amounts of air across the venous cannula into the patient's vena cava if the reservoir completely empties. C. The blood will instantly cool down. D. The cardiotomy filter will rupture. Answer: B. The negative pressure will pull massive amounts of air across the venous cannula into the patient's vena cava if the reservoir completely empties. Explanation: KAVD uses a centrifugal pump placed directly on the venous line to generate active negative pressure to pull blood from the patient. If the reservoir runs completely dry, the centrifugal pump will not stall like a gravity system. It can continue spinning, generate high negative pressures, and pull air retrograde from connections or draw gross air directly into the venous structures of the patient. What is the explicit safety purpose of the level alarm electronic eye compared to the level sensor auto-abort system on a CPB machine? A. The alarm eye adjusts the oxygen concentration automatically. B. The alarm eye provides an early auditory/visual warning to the perfusionist before the lower level sensor reaches the absolute volume threshold that triggers an automatic pump halt. C. The alarm eye measures the hematocrit of the blood. D. The alarm eye tracks the temperature of the reservoir. Answer: B. The alarm eye provides an early auditory/visual warning to the perfusionist before the lower level sensor reaches the absolute volume threshold that triggers an automatic pump halt. Explanation: safety systems are tiered. The upper level alarm is a warning system that alerts the clinician that reservoir volumes are dropping. This allows the perfusionist time to intervene, e.g., add fluid, reduce arterial flow, or request more venous return. The lower-level sensor is the hard stop that cuts power to the pump to prevent air embolization if the warning was unheeded or the drop was too fast. During CPB setup, a perfusionist notes that the coaxial tube design of the heat exchanger is constructed out of polyurethane rather than stainless steel. What is the clinical trade-off? A. Polyurethane has a much higher thermal conductivity than steel. B. Polyurethane reduces the risk of heavy metal leaching but has a lower heat transfer efficiency, requiring a larger surface area. C. Polyurethane completely eliminates water-to-blood leaks. D. Polyurethane allows the blood to be warmed to 45 C safely. Answer: B. Polyurethane reduces the risk of heavy metal leaching but has a lower heat transfer efficiency, requiring a larger surface area. Explanation: stainless steel offers superior thermal conductivity, allowing for rapid heating and cooling within a compact space. Synthetic polymers like polyurethane are highly biocompatible and eliminate any risk of microscopic metal oxidation or leaching, but because they transfer heat less efficiently than metal, the design must incorporate a larger surface area to achieve equivalent temperature control. What safety hazard is introduced if the gas exit port, exhaust, at the bottom of a membrane oxygenator becomes accidentally occluded by a surgical drape? A. The oxygenator will implode. B. Carbon dioxide and gas phase pressures will build up within the fibers, forcing gas bubbles across the membrane directly into the blood phase. C. The blood flow rate through the pump will immediately drop to zero. D. The heat exchanger will lose its water supply. Answer: B. Carbon dioxide and gas phase pressures will build up within the fibers, forcing gas bubbles across the membrane directly into the blood phase. Explanation: the gas phase of a membrane oxygenator must remain an open system with an unobstructed exhaust port. If the exhaust is blocked, the continuous flow of incoming sweep gas has nowhere to escape. Pressure inside the hollow fibers will rapidly exceed the hydrostatic pressure of the blood phase, forcing gas through the micropores into the blood, causing massive systemic air embolization. What is the primary safety function of an electronic ground fault circuit interrupter, GFCI, on a CPB chassis? A. To prevent the pump from losing power during a blackout. B. To protect the patient and surgical staff from microcurrent electrical shocks caused by fluid spills onto electrical components. C. To stabilize voltage fluctuations from the hospital generator. D. To regulate the speed of the roller pump motor. Answer: B. To protect the patient and surgical staff from microcurrent electrical shocks caused by fluid spills onto electrical components. Explanation: the operating room environment during open-heart surgery involves large volumes of conductive fluids, blood, saline, water lines. If fluid breaches an electrical housing on the CPB chassis, it could transmit stray microcurrents through the lines directly to the patient's heart, inducing ventricular fibrillation. GFCIs instantly detect current leakage and disconnect power to the compromised component. Why are modern CPB arterial lines routinely monitored via continuous inline blood gas monitors, CDI system? A. To measure the anesthetic gas concentration in the room air. B. To provide real-time, continuous readouts of pH, PCO2, PO2, and electrolytes without waiting for intermittent benchtop lab draws. C. To automatically adjust the pump's RPM based on metabolic demands. D. To check for systemic heparin concentrations. Answer: B. To provide real-time, continuous readouts of pH, PCO2, PO2, and electrolytes without waiting for intermittent benchtop lab draws. Explanation: traditional blood gas monitoring relies on drawing physical blood samples every 30 to 60 minutes. Inline sensors utilize optical fluorescence or electrochemical technology embedded directly within the circuit tubing to give the perfusionist second-by-second updates on acid-base balance and oxygenation, allowing for immediate adjustments to gas sweep or oxygen concentrations. What clinical finding is a direct indicator that the arterial line filter has become significantly obstructed during a CPB case? A. A drop in the patient's central venous pressure, CVP. B. A marked increase in the pressure gradient measured between the pre-filter and post-filter ports. C. A sudden drop in the sweep gas flow rate. D. A severe decrease in the water temperature of the heater-cooler. Answer, B. A marked increase in the pressure gradient measured between the pre-filter and post-filter ports. Explanation: under baseline conditions, there is a very minimal pressure drop across an arterial line filter. If the filter begins trapping large amounts of microaggregates, fibrin plaques, or small clots, the resistance inside the filter housing rises. The pressure before the filter, pre-filter, will climb significantly higher than the pressure after the filter, post-filter, signaling that the device is fouling and may need to be bypassed. During CPB termination, weaning, what circuit maneuver is performed to safely deliver residual circuit volume back to the patient? A. Running the cardiotomy suction at maximum speed. B. Controlled venting or chasing blood from the reservoir into the right atrium via the venous line or directly through the arterial cannula. C. Opening the pre-bypass filter line to full flow. D. Turning up the sweep gas to push blood forward. Answer, B. Controlled venting or chasing blood from the reservoir into the right atrium via the venous line or directly through the arterial cannula. Explanation: when weaning from bypass, the heart resumes its workload and requires adequate preload volume. The perfusionist slowly decreases pump flow while incrementally transfusing the remaining blood inside the reservoir back into the patient, either by allowing it to drift retrograde up the venous line into the right atrium or by incrementally pumping small volumes forward through the arterial cannula, carefully matching the patient's filling pressures and cardiac output.